Hello, I'm Blaine Radler, and this is a description of my newest invention. The idea was born after Hurricanes Irma and Maria ravaged Puerto Rico, leaving millions with no safe drinking water. In most cases, there was plenty of water, just no confidence that it was free of pathogens. The safest way to sterilize water, particularly water that's not completely clear, is by boiling, but this requires fuel, which may not always be accessible. The sun, however, is free and available, at least most of the time. Concentrating the heat provided by sunlight to boil water is an obvious solution, but unless the collector is the size of a king-size bedsheet, boiling a quantity of water sufficient to sustain a few people for a day requires constant management so that the sunlight can be focused on the container continuously for hours. This in turn requires hours of unbroken sunshine. My invention solves the need for uninterrupted sunlight by boiling small increments of water at a time and doing so automatically with no human management. On a cloudless day, where both mine and the traditional method might, for example, produce 1 gallon of potable water, on a partly cloudy day, mine may produce a half gallon, where the traditional method none whatsoever. The invention's automation is achieved by a simple but novel arrangement of check valves and an inexpensive Fresnel lens rotated on a polar axis of a gimbal mount by a small solar-powered motor. The following figures briefly describe the workings of the invention. I'll use the figures from the patent application to describe the operation. A mirror mounted on a simple gimbal directs the sunlight through a Fresnel lens, which focuses the light. A 1-foot square Fresnel lens made from plastic is as thick and light as a piece of cardboard and costs around $1. The gimbal mount allows the mirror to track the sun as it moves across the sky. The sunlight is focused onto a relatively small quantity of water in a boiling chamber. A few tablespoons of water can be boiled in a minute or so with a 1-foot square lens. Thus, only brief periods of sunlight at a time can boil an ongoing series of tablespoon-size water increments. Check valves, simple valves that let water flow in only one direction, control the filling and evacuation of the water from the boiling chamber, as we'll see next. Here we see the 3 phases of operation. Imagine that we start with the upper check valve open, the boiling chamber filled with water, and the lower check valve closed, since its cracking pressure, the pressure required to open it, is greater than the pressure of the water there due to gravity. Once the water in the chamber boils, the generated steam forces the lower check valve open and keeps the upper valve closed so that the boiled and sterilized water is ejected down through the lower valve. Finally, in the 3rd phase, once the boiled water is evacuated, the upper valve opens, allowing the next incremental water into the chamber. You may have heard that water should be boiled for at least a minute to sterilize, but that is to ensure that all the water in a large container reaches boiling temperature. In a cooking pot, for example, the steam bubbles may appear at the bottom while the water at the top is nowhere near boiling temperature yet. Bacteria and viruses are killed almost instantly at boiling temperature. This figure shows how the cracking pressures of the valves are selected. The distance of the valve to the top of the water determines how much pressure gravity induces, and the upper valve is selected such that it opens for any level of water, while the lower valve is selected such that it only opens for pressure greater than any level of water. And this figure illustrates the boiling chamber, which could be just a pipe with attachments for the valves at each end. The plate molded around the boiling chamber provides a surface for the focused sunlight to strike. Copper is a good metal for both the absorber plate and the chamber, since it has a high transfer coefficient. The absorber plate can be thermally linked to the boiling chamber with thermal paste. Here we see the mechanism for automatically tracking the sun. We first note that the sterilizer unit is positioned so that one axis of the gimbal mount is positioned north and south, so that, as it rotates, it tracks a path the sun takes as it moves across the sky from east to west. The other axis is positioned according to the height of the sun, i.e., according to the season. It's not easy to see in this figure, but we're looking down at the back side of the mirror. The Fresnel lens lies below it. These light sensors are mounted on each side of the Fresnel lens. As the sun moves across the sky from east to west, the light from the mirror moves onto the east side sensor. This small amount of electronics, powered by a small solar cell, detects this and activates a small stepper motor to move the mirror so that the sun is again shining directly on the boiling chamber. Finally, this figure shows an alternative approach to focusing the sunlight, where a parabolic mirror is used instead of the Fresnel lens. Although a parabolic mirror is generally more expensive than a plastic Fresnel lens, it is somewhat more efficient in delivering more of the sun's heat.